SSI Circuits Lab 2. Our team members include Cynthia Hoffman, Thomas Nielsen, and Jonathan Roberts. As an introduction, Thomas will find the sum of products for the truth table, then reduce it with Boolean algebra. He then will input the truth table into a Keymap, find the midterms and its equation. Jonathan then will evaluate the equation with AND, OR, and NOT gates and integrated circuits in Logisim. Cynthia then will evaluate the equation with NAND gates and integrated circuits in Logisim. Let's find the sum of products. The non-reduced sum of product is found when the output is true of the corresponding A, B, C, and D. You take the product and OR each statement together, making this equation. To reduce the sum of products, we apply Rule 3 to copy A0, B0, C0, D0, or A, B0, C0, D0. Then we apply Rule 6 to gather like terms, apply 5 to cancel out the bracketed items, and then apply Rule 3 to cancel duplicates. Let's find the Keymap. To find the Keymap, we need to find primarily the midterms. For Z0, you have midterms 0, 2, 8, and 10, which can be evaluated as B0, D0. Set 1 is midterms 0, 1, 4, 5, 8, 9, 12, and 13, which can be evaluated as C0. When you combine both sets, it is B0, D0, or C0.
Next, we will discuss the AND, OR, and NOT gates for the truth table. The reduced equation can now be represented using AND, OR, and NOT gates. To do this, you need 3 inverters, 1 2-input OR gate, and 1 2-input AND gate. The B, C, and D are all inverted. The inverted B and D run through an AND gate. The result of that and the inverted C run through the OR gate. We note in this that the A input has no bearing on the output. We can now view the same truth table using the 7400 series TTL ICs, TTL being the transistor logic and 7400 series being the chips first manufactured by Texas Instruments that are now in wide use. This diagram, we use the AND 7408, the OR 7432, and the NOT 7404. We will note that not all of the gates on the circuit are needed to make this logic work. Now taking a closer look, we can see the details of each chip in the 7400 series. The 7404 inverter, you can see, has 6 inverters on the chips. For this truth table, we use 3 of those inverters and then the power and the ground. In the 7408 quadrant AND, there are 4 AND circuits. We used 1 and the power and the ground. And then the 7432 OR, we again used 1 of the possible 4 circuits and the power and the ground.
I will be talking about NAND gates in this presentation. NAND gates are functionally complete. Whatever you can do with any other gate can be done with just NAND gates. To convert our AND OR function to a NAND function, we need to take our minimized equation, B0 D0 plus C0, and flip it inside out with De Morgan's rules. That gives us 2 separate NAND expressions, first being B0 D0 NOT, and if we use X to hold the place for that expression, just so that we can see things easier, we end up with XC NOT. We also need 2 NAND gates to use as inverters for both B and D. We end up with B0 D0 plus C0 equaling B0 D0 NOT and C NOT, which is always best to be double checked with a truth table. This is the inside of the 7400 quad NAND. This IC has 14 pins, 1 for power, 1 for ground, and 12 to accommodate the 4 NAND gates. Using just this one IC, we have all the gates we need. On a minor note, although fun to play with, I found the 7400 pieces very easy to break. Saving the file and opening it again fixes the problem. In conclusion, this project was fun. It showed the whole process from truth table to something that could work in real life. It showed us how real-world ICs look, as well as how things look on a gate level, and how we can use the build of the ICs to make our designs more efficient.